Hi, everyone. First of all, let me thank you to the organizers for inviting me to here to speak, and also for getting the main venue in here, because thanks to that, my anxiety is hitting like the roof, and I'm pretty nervous. So, about memory management. What I'm going to talk is, it's like the 101 of memory management in Python. What I want to show you or teach you, or what I want from you is to have far more like known unknowns than unknowns that you had before. So let's start with a simple question. Why should you care about memory management? Like most of the time, like the honest answer is you probably don't have to. Because most of the time you will not reach the limit of the memory in your machine. Because at least for us in Kiwi, we release like very often, like 10 releases per day are quite normal. And the thing with the memory management and memory consumption is that the memory grows with the time. And when you do 10 releases per day, you reset the memory consumption like on every release. So you probably don't have to care about it. But there may come a time when you will have to. So you may ask then, why do you care? Because, I mean, I never used anything from this presentation. I never use it in a real life. So why do I care? Well, first thing is that I like to learn new things. When a year goes by and I look back and I'm like, yeah, what do I know what I didn't know a year before? And when there is nothing new, you know, there's like some sort of stagnation. You don't learn new things. You are not becoming better. So this is the first thing why I decided to give this talk, because I was always interested in memory management in Python. And also, somebody may ask you about it in a job interview, because that's where things like this happen in the job interview. Like, you probably will not ever need to know how dictionary works, but people are going to ask you that on job interviews. And also, we had this merge request, and we had in the past problem with memory leaks. And this guy, he tried to find those leaks, and he was trying to find them using getSYS.GETSIZEOF, which doesn't really work. So that was another reason to create this talk, to show people like how the memory management works. And also, we have, when I first met our CTO, it was in EuroPython. We were attending a talk, and there was this guy saying like, yeah, Python never releases the memory back to the system. And he was like, yeah, you did know that, right? And I was like, yeah, maybe, I guess. I went with the flow and I said, yeah, sure. And it's not entirely true. So let's start with the basics. Everything's object in Python, and that's a very important statement, because on top of this, it's the memory management is modeled in Python, like how it behaves, and all of the trade-offs which were chosen are based on the fact that everything is object in Python. And when you look there on the right side, this is how every object looks like. This is the fields, like these fields every object has in Python. The first field, the PyObject head extra, is just some debug field, which I think is not really even enabled in a classic compile. And you need to pass some flags to have this defined. The another one, which is very important, is the object reference count, and I will tell you more about it later. And the third one, the pointer to the object type, is just the object itself. So, memory management. This is the overview of memory management in a system using Python. Like you can see at the bottom, there is like a physical memory, the OS specific things, and then there goes the malloc, which is a very basic thing if you have a program in C. And on top of that, there is a Python raw memory allocator, which is managing a heap in a Python. This is the thing which is taking care of, which is making sure that heap has enough memory. And then there is a Python object allocator. This is something we are going to talk about. And on top of the allocator, there are Python's objects in the memory. So the most interesting layer for us for this talk is the +2 layer. And also these layers, this is just copy-pasted from the actual code in CPython. There is also a link at the top. So I think I will share my slides somewhere. And if you are interested, you can go to the OpenMalloc and you can find these layers also with some extra additional info. So how is memory actually allocated? Well, objects in Python are divided in two main types. These are objects which are greater than, equal or greater than 512 bytes, or smaller than 512 bytes. The greater objects, these are managed by the malloc, which is not malloc in Windows. Windows has a different manager for memory, but it doesn't matter. And what are we going actually talk about? Because the greater object, that's very boring stuff. We're going to talk about the smaller objects, because most of the objects in Python are the small objects. So Python is using something which is called simple segregated storage based on array of free lists. This, again, I just copy-pasted from the code. This consists of 3 levels of abstractions. Like the bottom abstraction is block. Blocks make pool, and pools make arena. And this is like sort of trade-off which was chosen for Python because of the amount of objects in Python. This is very efficient and very simple technique for Python to manage objects. So let's start with a block. So each block stores exactly one object. And as I said, the biggest size for the object is 512 bytes. So these blocks are divided into categories. And there are 64 categories, and each category is multiplication of 8. So if you have an object and it has a size of 6 bytes, it belongs to the 0 size class, which is 1 to 8 bytes, because block has 8 bytes. And it doesn't matter, like, it only matters if the object fits into the block, and even that the object has a less, like, smaller size than the actual block, it takes the whole 8 bytes. So those are blocks. And then there are pools. So pools are like lists of blocks. And each pool contains only blocks of the same size. And the size of the pool is 4 kilobytes. That's like one memory page in system. And each pool can be either full, empty, or used. And full, that's, I mean, all of those categories are self-explanatory, I guess. You may only wonder like why there is like the empty, when all you need is to know it is used and you can put more data in it. Well, the empty flag is used for arenas, and I will tell you more about it at the next slide. And also, there is a really great opportunity to become an open source contributor, because I would really like to see another category there, and it would be category of dead pool. So if you manage to find a reason why there should be a dead pool used, please submit a merge request to Python. So arenas. Arena is a chunk of memory which is allocated on a heap. So if you remember, it was the +1 layer, that's where the heap lies, and the heap is and the RNA gets the memory from the heap. So each RNA can hold 64 pools, and this is the very important statement. Only RNAs returns memory back to the system, and only if all pools in it are empty. So this is the real truth about Python not returning memory back to the system. It's like, I mean, it really does return the memory back, but it doesn't happen so often that all the pools are empty. And really cool thing in Python is the Python malloc stats environment variable, or the SYS.debug malloc stats function, which will print for you the actual usage of all the blocks and arenas and memory. You can see it right here. It's not very big, but you see here are the blocks, and there is like blocks in use, available blocks, and blah, 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 things like that. So you can either use the environment variable or call the function to see this output. Blah, blah, blah. Okay, so, this is my favorite thing. This is something which is running on Twitter every now and then. This is a thing called small integers. And you may have already seen it. It's like the identity trick on integers. Like when it's the 2 is 2, it returns 2, but when you give it some really high integer number, it returns a false. So the thing is that Python, for the performance reasons, at the start of the interpreter, it allocates all of this integer from -5 to -5 including to 257 excluded, and it pre-allocates the memory for those. It creates this integer and it uses them. These integers are being reused. They are not. These objects are being not created again. So once these small integers are created, every time you use any number from this list, it is not being created again. And another very similar thing is there in a place for strings. It's called sys.intern. And as you can see, when you create two same, obviously, strings and you compare them, it returns true, like the identity for the object. I guess I should probably explain the difference between is and equals, but is compares like the allocation of objects, and equals compares whether the objects are same. So how string interning works? There is like very important statement that interning happens only at the compile time, and only strings that are composed of ASCII letters and ASCII chars are limited to letters, digits, and underscores. And the thing about the interning happens on the compile time, you can see at the next statement where the join is being used on foo, on the list of characters foo 00. And when you compare join to second, it returns false, because the string is created at the execution time and not at the compile time. As in opposite to, and the second thing is bytecode optimization plays a role too, because when you look down, like the foo plus bar is foo bar, it returns true. That's because the byte optimization at the compile time actually makes sure that foo plus bar is actually foo bar, and it's not being run at the execution time. It's already stored as a foo bar. And the next example is using chars which are not permitted. And the last one is actually a function which you can use to force sys.intern on any string. Also, there is a link to the article which goes into like bigger depth of this, and you should read it if you are interested in this. So, as I was speaking at the beginning, my colleagues tried to use the sys.GETSIZEOF to get the actual memory usage of some objects, which is not good because if you look at the examples, you get the list of integers and list of strings. And when you call getSyzOf on both of them, it returns the same number. Even though obviously string and integer has a different size. And that's because the getSyzOf returns only the object size. Like, for example, list is objects by itself, and the objects which are stored in the list are only pointers to these objects. So pointer to string has the same size as a pointer to integer, and that's why it returns the same size. And it's very important to remember this. Oh yeah, I can show you the example of debug malloc stats, because given all the informations I provided, you should be able to answer question for this. I will create a list. The above, there is the blocks usage for the previous, before the creation of lists. So I will create a list, or not. Unexpected indent, cool, thanks. It's like always a bad idea to type live. And I will call debug malloc stats again. I will try to copy this, which is not really easy. At least I don't know how to copy stuff on Mac. I really hate it. Oh no. Yeah, I fucked up. Right. So yeah, this happens to me quite often. So let's see. I give it another try. If I manage to scroll to where the output was, or here it is. So fingers crossed. Please work. So 13 soon, 3. Yeah, nice. You can clap if you want. You don't have to. Thanks. So this is a simple diff. And I have a wrong diff here. But it doesn't matter. Okay, never mind. The thing was that what should be shown here, and I think it doesn't work because I passed it there, the other output. Yeah, I don't know how. Oh, maybe. Cool. So what should be supposed to be here, there should be only 2 changes in blocks in use. And it would be, I think, 10, line 10 or 11, and line 6 or 7, I'm not sure. And both of these would be incremented only by 1 and nothing else. And so my question would be, why that? Like, why only 2 blocks were created for a list of size 4? Anybody knows? I've created here is the object I created. Yeah, you here. Yeah, you are talking about small integers. Yeah, so small integer already exists. Therefore, they weren't created, and the only thing created was the list. But what about the other block? Because there were 2 blocks.
List has 2 memory allocations.
What?
List uses 2 memory allocations, one for the list and one for the page item list.
I actually think, I'm not sure, I'm asking. What?
Can you repeat the question?
Yeah, there were incremented actually 2 blocks. 2 different blocks were incremented when the list was created. And one block is the list itself, but what is the another block?
List memory for the items.
Yeah.
From the list.
Yeah, but the thing is, it was in a different size when I created the same list with a different variable name. So what I think the other block is actually a variable name. But I'm not sure. But probably you may be right.
Well, you assign it to a variable, so it does new entry doubles.
Okay. So that was the example. Let's go to collecting garbage. Do you know this guy? He collects garbage. It's Tony Soprano. Okay. There are two main methods for garbage collection in Python, and the first one is reference counting, and another one is generation cyclic garbage collector. So how are these being used? Reference counting. That's very simple. Like if you remember from the beginning, the object itself, it has the field name object reference count, and every time you use the object, the reference count gets incremented by 1. So once the reference count reaches 0, the object gets destroyed. It's very simple and very efficient. And here you can see like the examples of get reference count. And there again is a tricky question why the A reference count is 130. This was being run at the start of the interpret. And the guy in the white probably knows why. Because of the small integers. They are being used everywhere. So there are like 130 references to the integer 2. And the other tricky question is why foobar, even though it wasn't like created anywhere before, it has the reference count of 2.
Because get count requires its own reference.
Yeah, exactly. So there are actually two.
Repeat the answer.
Oh, repeat the answer. So there is defined the foobar string. It's the beginning of the program. But when I pass it to the get ref count, it outputs that the reference count for the foobar string is already 2 for that variable A. So the question is, why is that? And the answer is because when you pass the A variable to the get reference count, the another reference is being created. And that's why the 2. So the other thing is the generational cyclic GC. That's something that reference counting cannot, and that's finding the cycles. It runs periodically. There are like 3 generations, which is not true anymore since Python 3.7, but I will get to that. And each object starts in the first generation and then moves to others based on whether it was changed somehow or collected or not. And the lower generations are collected more often. And this is very important. It freezes the execution of all of the code. Like when GC runs, nothing else runs. And I mean, yeah, it's because of GL, but the garbage collector has like the upper hand. And you actually can see the cyclic reference on the right side. I'm using C types to get the reference count. And here you can see the list, which I append then to the original list. And when I run the del for list, the address of the object is still alive and still has some reference counts. And that's because there was a cycle which reference count didn't know about. And when you run the GC, it will output the number of bytes, I think, or objects which were freed or are trash or something. And then when you run the reference count again on that object, you will receive the correct 0. So del versus the dunder del dunder. So del doesn't delete the object. That's very important. Del only decrements the reference count for that object. And what dunderdel does is that it's being called on the object destruction. And very important thing here is that you don't really want to use dunderdel dunder because it brings a lot of magic into the code, and also you will break the cyclic the discovery of cycles for garbage collector. Garbage collector will ignore your object with dunderdel dunder specified and will leave the cycles discovery up to you for that object. And so, in a short, unless your name is Victor Stinner, you are not using the dunderdel dunder. So, removing cycles. As I told you, the garbage collector has like a really big impact on the system. So what you really might want to do is get rid of the cycles. And to get rid of the cycles, you need to find out the cycles. And for that is really good Python module called object graph. I don't know how to say it, so just read it. And what it does, it will create this cool graph for all the objects inside your object. And then you can use the weak references to get rid of the cyclic references. As you see at the beginning, there is like b equals a, and when you delete a, the b still lives. And then, if you would instead create a weak reference to a for b, and you would delete a, then the b would be none. It would be undefined because of the weak reference. Or the other thing you can do is disable the garbage collector. What is something that Instagram did, and they did have to enable it again, because as I told you, the thing with Python is that when you have your app running, at least we are using Unicorn with forking, so we run the master process and then we spawn the child processes from the master processes. And what Linux does is that unless you are writing to the memory is shared between the master process and the child. Unless you are writing to that size of the memory, then the memory is copied for the child. And the problem with Python is, it's called copy on write. But the problem with Python is that it does actually copy on read. That anytime garbage collector is being run and the object reference count is being increased because of some list and some structure in a garbage collector, the object reference count is being increased. Then even though you are not writing to those objects and they are being only read, they are actually being changed because of the reference count. And therefore the objects are being copied and copied and copied again. So what the Instagram did was that they disabled the garbage collector, but later, I mean after a year maybe, with the huge number of new features and stuff, they find out that the trade-offs, the saved memory was actually diminished by all of the features and the size of the code base, that it was much more feasible for them to enable the GC again because they were losing a lot of memory. So what they did instead is they created a what was the name? Wait. Yeah, generation. Yeah, they created a new generation. For objects. And you actually can call this GC. It will be added in 3.7, or it is already, and you can run the GC freeze to move all your objects into the fourth generation, and then those objects are never touched again by the GC. And then you save, those copy on reads. They are not happening because GC is not accessing those objects, which is like, for me, it's really cool, and that's like the best feature in Python 3.7. So, about memory tools, how much time do I have? Not much, I guess. Okay, yeah, QA. Okay, these are two basic tools you can use for tracking memory. And the first one, this is an example of memory leaks. It's called Pimpler, and you can initialize the Pimpler, run your function when you think that the memory leak is happening, and then you run the diff between those two sessions, and it will output you like how many objects were created and not destroyed after the function run. And this may happen if you are creating objects inside a function to the global state of your program or something like that. And it may come handy if you will sometimes hunt for memory leaks in your Python code. The other thing is transmalloc. This was added to Python 3.4, and it's a work of Victor Stinner. And it can output the memory usage of blocks of objects per file. And it again may come handy, but I guess there's no time to show it or something. So that's everything. Is there time for questions?
Yes, it is time for questions. Thank you, Robert. Unfortunately, we don't have any questions at Slido.
Oh, cool. Thank you very much.
So, does anybody have a question out of Slido?
No.
There's one.
Question? No. Please be kind.
Yeah. Hi.
Hi.
You said that we shouldn't use the _ del for deleting the objects, but what if your object is using external interface which you need to close or deallocate or anything to do with it?
Yeah, almost everything you said, I didn't understand, sorry. Can you repeat the question more loudly?
Okay, so I will try to one more time. You said that we shouldn't use _ del to delete objects, but what if the object uses some external interface or anything which needs to be handled during the object deletion?
Yeah, I think I don't answer. Okay, if some other object is using some other interface which...
The question is, if you actually need del to do some cleanup, what do you use?
The del.
Yeah.
Okay, I never needed it. Never, like never. You don't need it. I don't think so. You shouldn't need it. It should be deleted from Python, I think. Any other question? Oh, there is raised hand.
Hi. So at the beginning of your talk, you mentioned that somebody made the statement that Python doesn't release any memory back to the operating system. Yeah. But given all your slides, what's your conclusion? Does Python give it back to the operating system, or does it consume memory and never give it back?
Yeah, I think it does return the memory when all the arenas are, like all the pools in the arenas are freed, then the memory is returned back to the system. That's what I get from my talk, at least. Thanks. Any more questions? No? No one? Thanks.
I can't. Oh, there's one.
Oh, no.
This is more a rhetorical one. I don't really require an answer. It's more like what you can learn next, because you were saying you're learning the...
what I'm learning next? Yeah. The next thing...
Because you want.
Oh, yeah. Next thing I'm learning is actually Golang. I'm switching from
what
Python to Golang.
What I wanted to say is you don't really need... well, by redefining the del method, you don't really have to break the Python.
Okay.
There are even contrary functions like init, and you can like for more, and if you redefine all of them, you still can support the garbage collecting.
Yeah, sure. I'm not saying something against it. I mean, I think you don't really need to use it. That's it.
Right, we're almost out of time.
One more
question. So please make this one quick. We have
really
less than 1 minute left, and I'm not helping.
It's actually just a comment. Just remember that del is actually safe now because...
del actually what?
Del is actually safe now because they added finalizers to Python 3.5, do you know? 4, 5,
so
something?
It's safe to use now?
Yeah, it should be.
So you actually can use the del. Sorry. Dunder is very cool, and you can use it again. Yeah, don't use it.
Right. Thank you, Robert.
Yeah, you're welcome.